Greetings and salutations, magical chemists. Let's talk about electrolytic cells, which are shockingly awesome despite being thermodynamically unfavorable. Now, because they are thermodynamically unfavorable, they must have a positive Gibbs free energy and a negative cell potential. And because an electrolytic cell is not happening spontaneously, it will undergo a redox reaction only if you apply current or voltage source. Let's compare a voltaic cell and an electrolytic cell, made by combining zinc and copper. Now, in a voltaic cell, which is of course spontaneous, electrons of their own free will flow from the anode to the cathode, where the anode is negative and the cathode is positive. If you wanted to force them against their will to go backwards, that would be an electrolytic cell. Notice the voltage source that's powering this non-spontaneous redox reaction. What's interesting about this is that switching the direction of electron flow will actually end up switching the charges on your anode and cathode. And did you notice, of course, that even the anode and cathode switched places because now opposite things are being reduced and oxidized. But now the cathode, which is still being reduced, actually has a negative charge, and the anode, still being oxidized, has a positive charge. So the charges actually flip their signs. To be honest, most of the time, an electrolytic cell actually happens in a single container. It's not split between two containers like we see in a voltaic cell. We just did it for this picture, so you could make the nice analogy. And then, I think I said it, but I'm not sure, but I want to make sure you're aware. Anox and red cat still work. They're still accurate, thank goodness, in electrolytic cells, just like voltaic and galvanic. Okay, let's actually look at a table that kind of summarizes the similarities and differences between the spontaneous and non-spontaneous electrochemical cells. Well, we know that our galvanic cells are thermodynamically favorable, so they have a negative delta G, positive E cell, and a K greater than 1. Electrolytic cells are the opposite of that. So they have a positive Gibbs free energy, a negative cell potential, and a K less than 1. Now, galvanic cells, of course, are spontaneous in the forward direction. The electrolytic cells are actually spontaneous in the reverse direction. Voltaic cells are usually separated into two half cells, so you can actually get a flow of electrons. You get electricity from that. But most of the time, electrolytic cells will be in a single container. You can do it in two containers, but it's usually just in one. A galvanic cell, of course, is a battery, but an electrolytic cell needs a battery. It has to do with the types of energy being transformed. A galvanic or voltaic cell turns chemical potential energy into electrical energy. An electrolytic cell, you're taking your energy source, your voltage, and turning electrical energy into chemical potential energy. Now, in a galvanic voltaic cell, as you know, the electrodes are usually, or at least often, made of the metal used in the half reactions. But electrolytic cells most commonly use those inert electrodes, platinum or graphite. For galvanic cells, electrons are supplied by, the species being oxidized, of course. But for the electrolytic cells, they're supplied by the external battery at the cathode. And then there's the charge we talked about. In a galvanic or voltaic cell, the cathode is positive, the anode is negative. But electrolytic cells flip that. A quick trick to help you remember is EPA, electrolytic equals positive anode. Okay, so far we've been talking about kind of generic electrolytic cells, but now let's go ahead and take a look at some specific applications of electrolysis that you will need to know. Well, the first one is electrolytic cells, but electrolysis is a specific type. In electrolysis, this is the process of using electrical energy to break apart a compound. So this is really useful. You can take a compound and break it into its component elements. You might be wondering, okay, but why would we actually want to do that? Well, for instance, the electrolysis of water is used to generate hydrogen for fuel cells. And I'm sure you remember, in the chemical reaction for water, you have 2 moles of hydrogen gas and a stoichiometric ratio for every 1 mole of oxygen gas. So that means in the electrolysis of water, you're literally going to be making twice as much hydrogen as you do oxygen. Funny story, the water's being dissociated at the same rate, so the same rate of speed, but twice as much hydrogen will be produced as oxygen. Now, the electrolysis of water is so common that it actually can be quite helpful to know it's starting with water to see what's being oxidized and reduced, but you actually might want to you either have to be able to derive or you have to memorize the half reactions for oxidation and reduction in this electrolysis of water. So let's take a look at the picture showing this in action. So you'll notice that the reaction shown at the top is exactly the same that was in the boxes, but it's just visually seeing. So notice you've got a battery and you're literally just plugging a battery into water, which is weird but totally a thing, and then you make bubbles. And the bubbles on your negative end are producing hydrogen. Notice, twice as much as the oxygen being produced from the positive end of the battery. Stoichiometry is a beautiful thing. Okay, let's go ahead and answer just some quick practice problems, because as you can probably tell, the electrolysis of water is really commonly used and thus really commonly tested. Luckily, these are all questions that you have enough information to be able to answer. So you're going to try them, and then when you are ready to check your answer, unpause the video. Well, crazy story. Did you realize in the dissociation of water, water's being reduced? But wait, water's being oxidized too. That's kind of weird. Remember, you have to identify the compound that the oxidation or reduction is happening to, but we know individually it's the hydrogen within the water that's actually being reduced. Because hydrogen had a +1 oxidation state in liquid water, but when it forms hydrogen gas, it goes to a 0 oxidation state. Which means, of course, the oxygen in water is getting oxidized. Oxygen hates to be oxidized, which is why this is a non-spontaneous reaction. Oxygen starts at a -2 oxidation state in water, but then, of course, it goes to 0 when it forms the oxygen gas. For the very last one, this was actually just a cute little stoich problem, because we know that we collected 2.7 milliliters of O2. Just like you can do a liter to liter gas stoich, you can do a milliliter to milliliter. It's the same mole to mole ratio. Because, of course, for every 1 mil of O2, you get 2 milliliters of hydrogen. So it should not surprise you that we produced twice as much hydrogen as we did of the oxygen. Okay, so that was electrolysis, most specifically electrolysis of water, but there are other applications of electrolytic cells. Let's look at something known as electrorefining. This is the purification of impure metals, often ore, by using electrolysis. For this type of electrolytic cell, you want to set up your anode as the impure metal, your ore. I remember an ox is, of course, your anode is oxidized, is an ore. The A and O still go together. That means the cathode, the fat cat, that's going to be the one where the pure metal will be deposited, of course, because that's the one gaining in mass. Now the solution, the electrolyte that everything's floating in, needs to contain the cation of the metal that you want to purify. It's actually kind of gross as this runs. So you notice how you have that impure sample at your anode? You get this sludge, it's literally called a sludge, at the bottom of all the impurities that build up at the bottom, as of course you're pulling out, in this case, the pure copper and reducing it on the cathode. Okay, we've talked about electrolysis, we've talked about electrorefining, we have one more you have to know, electroplating. Electroplating is when you apply a thin layer of an expensive metal onto a less expensive one, either for structural reasons or cosmetic reasons. The object that you want to plate or cover in the thin layer is the cathode, right? The fat cat wants to get the mass. And then just like in electrorefining, your electrolyte solution should contain the cation of the metal that you want to plate. And the best anode is actually made of the same metal that you're plating onto the object. So in the example off to the right, you've got an anode made of pure silver, and notice you've got this ring that we're coating in a thin layer of pretty silver. All right, let's go ahead and try a practice problem down at the bottom of the page. Well, I think you know what I'm going to say. I think you should try the practice problem. And then, when you're ready to check your answer, unpause the video. Okay, first in part A, we wanted to identify the anode and what it's made out of, and the cathode and what it's made out of. So we had to figure out where they were and what's going on. Well, first we had the positive and negative charges. Remember, electrolytic is a positive anode. So the anode was positive, the cathode was negative, and the electrons still flow from the anode to the cathode. Well, now we have to figure out what the anode and cathode are made out of. In this case, we were taking an ore and we were trying to purify it with electrolysis. So remember, the anode, where the oxidation takes place, is where your ore or your impure gold would be found, which means your cathode should be pure solid gold electrode. And that's where you're going to start plating all of your new fancy purified gold that you are making. So over time, the ore is actually going to be eaten away, and it's getting smaller and smaller, reducing in mass, and of course all the sludge will start to fall at the bottom. Okay, I think that takes care of all the things from part A and the things from part B. I guess part B and part A are redundant, whoops. But we still have part C, a possible electrolyte for use in the solution. Well, first remember, we want the cation of the pure metal. So notice up here, this is where reading the beginning is always helpful. It told you that assume gold, in this case, is going to form a gold 3 plus cation. So we must need some gold 3 plus cations floating around in solution. But that doesn't actually answer part C, because we need to know the electrolyte, and the electrolyte is the full salt. So we need a salt containing a gold 3 plus cation that is 100% soluble. So I just said gold nitrate. There are other things that are 100% soluble, but you have to know that nitrate is 100% soluble, so I figured that's a good one to pick. And that's it. Those are all the notes about the applications of electrolysis and electrolytic cells. You're going to want to move on to the next video to learn all about the fun and exciting math we can do with electrolytic cells. It's going to be ever so much fun. I'll see you there.